In the last video, we have seen how to use a feed-forward neural network to perform a classification task. Let's see what we have learned last time. When we are talking about convolutional neural networks, a classical feed-forward neural network usually is referred as fully connected or FC layer. So basically, we have an input, here x, which through an affine transformation via the matrix WH and a nonlinearity f, we can get a hidden representation H. We can use that hidden representation in another affine transformation with the WY matrix and a nonlinearity like the G function in order to get our final output y hat. So we have that our H vector, the hidden representation, it's a warping of an affine transformation of the input x, and the output, the y hat, it's again a warping, maybe a different warping, of an affine transformation of the hidden vector H. And the warping or nonlinear functions f and g could be like the positive part, which is called also ReLU, the rectified linear unit. Could be a sigmoid function, a tan h, a hyperbolic tangent, or even a softmax. So let's now explode these vectors representation into their separate components. So my input now, x, is going to be represented here by those 5 circles. Each circle corresponds to one of the 5 dimensions, in this case, of my input x. Then I'm going to have my hidden layer, here represented with the 10 circles, and in this case, h is going to be of dimensionality 10. Then I have perhaps another hidden layer, which I'm calling h2, and one more, h3. Finally, I have my y hat output, which is the last layer of the network. Each of these layers can also be called activation. So the first one is going to be the activation of the first layer. So the first layer of a neural network, it's its input layer. And here I represent it as the vector A1. The second layer activations are represented with the A2. The third layer, A3, and so forth. So the Lth layer, the generic L layer, is going to be represented as AL. And the final layer, given that we have capital L layers, is going to be A capital L. To go from the activation A1 to the activation A2, we can use the W1 matrix. To go from the activation A2 to the A3, we can use the W2 matrix. And so on. So from A3 to the next is going to be the W3, and at the generic L layer, we are going to use the WL matrix. So let's now focus on a jth element of the activation of the second layer. So, for example, this one. So we have that the jth element of the second layer activation is a warping of the projection or of the input x towards the jth row of my matrix. So this guy is the jth row of the W1 matrix because we are actually going from the activation of the first layer to the second layer. Here we have a multiplication of a row vector and a column vector. So it's basically a dot product of the two vectors, which is what the geometric projection of one vector onto the other. In mathematical terms, this means I will have to multiply the first component of the jth row with the first component of the input, the second component with the second component of the input, until the last component of the row vector with the last component of the input. Sum all together, sum also the bias. So graphically, we have here our input, our 5 circles, and then we are going to have that each of these inputs are multiplied by a specific weight, Wij, and it's going to be giving me my first activation here of the second layer. For the second activation of the second layer, it's going to be the same. So I have to do again all this summation of products and so on. So to get the full second layer activation, I will have to multiply many times the input with some weights coming from the W1 matrix. In a similar way, in order to get the activation of the third layer, I will have to multiply the activation of the second layer by some specific weight and then apply a warping, a nonlinear function. And this was done through the W2 matrix. Now from the third layer, I'm going to be going to the fourth layer, multiplying again each value with the values from the matrix W3, and so on. So to get the last layer, again, we are going to be using all the previous values and that are contained in the matrix WL. So let's consider now, for example, an input that could be an image. So we are going to have an image here which has a height of 256 pixels and a width of 256 and a depth of 3. So it's a RGB, it's a color image. So overall, if you multiply these three numbers, you're going to get roughly 200 million, which means you're going to have 200 million dimensional input vector. Yes, that is correct. So X, it belongs to R of 200 million. Now think, you're going to have to do how many multiplications? You're going to have to do 200 million multiplications for each of the activation units of the first layer. And let's say the first hidden layer is perhaps as big as the input layer. So we are going to have 200 million times 200 million. So yes, that's right. So if you had 200 million input, and then perhaps you're going to have a hidden layer of, again, 200 million, you're going to have roughly 40,000 trillions or 40 quadrillion operations. That's a lot, trust me. Your network will never finish to compute your input. So let's see how we can actually reduce the number of computations and accelerate the convergence of this network.